All right, the first thing is the question about lab tomorrow. What did I say about lab tomorrow? What are we going to do? Anybody catch that? Are we going to start the wet lab tomorrow?
No.
Yes? No? I said no, right. I said we aren't going to start the wet lab tomorrow. I'm just going to go over it, right? And so that's, but you know, that's why it's easy to miss stuff during class, so that's why I try to record it. I didn't post the recording though, but just think, you know, the people who caught the information will have an advantage over you when things get more competitive, you know. So you want to think about that. Try not to miss any information. So we're just going to talk about it. It's going to be a long lab. We aren't going to finish the lab on Thursday. I didn't say that. What did I say about this lab that's coming up? It's multiple days. And do you guys recall how it's going to be broken down?
Yeah.
You're going to work individually or in groups for the whole part? Yeah. And then individually. You're going to... and are you going to have your lab manual available or no lab manual? Well, initially you'll have your lab manual available, but after that, no. You got to go straight off your notes. All right. Well, that's a lab. Any other questions?
Do you know if they got the lab manual back with the footstep? They're sold out.
Yeah, maybe not. Let's see. If you go, you know, if you go to Doucette's webpage, Professor Doucette's webpage in Chem, he hasn't posted up. You can download it.
And you can just print it out.
Yeah, just print it out. They happened once before, so I put them up there, but I'm pretty sure they're still up. Okay, other questions? What are we having tomorrow? The exam. The exam will be the second part of lab tomorrow. Exam on chapter 15. Any questions?
43, chapter 15.
43. Just read out the question. Okay, stop right there. What was the metal? I missed it.
Cadmium.
Cadmium? Okay.
Cadmium metal is added to 0.35.
Cadmium, is that solid? AQ? 2 plus?
Yes, cadmium.
If they just said cadmium, what would you assume? Solid. It is added to what?
Added to 0.35 liters of the aqueous solution in
0.35 liters?
Yes.
Just 2 sig figs?
0.
0.350 liters, 3 sig figs. That makes a difference.
Chromium 3 plus is 1 mole energy.
All right. Is it just 1 sig fig?
1.00.
Yeah. We got to make sure we keep track of the sig figs in all our calculations. And so far we have 3 sig figs and everything.
What are the concentrations of the different ionic species at equilibrium? What is the minimum mass of cadmium metal required to establish this equilibrium?
Okay.
The Kc is 0.288.
Well, Kc is going to be for a specific reaction. So did they give you the reaction?
Yeah.
Yeah. If you look at this, you know, metals are reducers. And, metal cations can be oxidizers. So what does it go to? Cadmium, probably cadmium 2 plus and chromium 2 plus. And then we got to balance this. We'll need 2 and 2. And then they give us a Kc of what?
And 0.288.
0.288. So cadmium is a solid. So what do we do with solid? ignore it, but you know, technically we don't ignore it completely because if you don't have any cadmium, then this reaction is not going to happen. And so what we assume is we have just the right amount or we have an excess of cadmium. Even if we have an excess of cadmium, it doesn't make an impact. Like say if I put in 10 pounds of cadmium, you know, in this, it doesn't matter because usually when you put in 10 pounds, you'd expect the reaction to be more violent, more vigorous, but it doesn't change its concentration. What's going to happen is as long as we have excess in there, it should go to equilibrium. However, chromium 3+, you know, if I add another gallon of chromium 3+ and it's 1 molar, that's not really going to change its activity, right? Let's say I add 1 more gallon of 1 molar chromium 3+. Does that change its activity? No. The only thing that changes its activity is if it were more concentrated. And so if instead I added like 6 molar chromium 3+, that will certainly change its activity because it's going to be a heck of a lot more concentrated. And that concentration changes will impact this. We know by Le Chatelier's principle it should shift it one way or the other. So the more concentrated I make the reactants, it should favor the products more. Or at least shift to the products more. In this case, it looks like it favors which side? Yeah, but it's difficult because, you know, over here we only have 1 chromium in solution. Over here we have 2 things in solution. So it's difficult to make a comparison. So when you see a number like this, you just say both sides. You expect an equilibrium established. Well, anyway, we know the chromium 3+ is 1.0 molar. The cadmium is 0. And so this is just your standard ICE table. So you get minus 2x here molar, 1.00 minus 2x molar, plus x molar here. So we get x molar here, plus 2x molar here. How many people got this problem? Okay. And is there a specific place you got stuck on this?
My problem was when I reached the part where I did successive assumption.
You use successive approximations for this, okay? Let's take a look at what we got going here. So we got cadmium 2+ at equilibrium times chromium 2+ squared divided by chromium 3+ squared. And so we'll just plug everything in here. This is going to be x times 2x quantity squared divided by 1.00 minus 2x raised to the 2nd power. And so this is going to be a cubic equation. So you use successive approximations for this? Yeah. Okay. Yeah, a cubic, well, there are 2 things. You know, the calculator will solve cubic, you know, that calculator I gave you. So you could get it in cubic form. Ax cubed plus bx squared plus cx plus d equals 0. And then you plug in a, b, c, and d into your calculator and you can get it. That's legal because the calculator is okay. For 4th order, since this is legal, then I'd probably make it 4th order, so you're forced to do a successive approximations or something like that. Or, you know, before trying successive approximations, you should have tried what? Simplifying assumption. Did the simplifying assumption work or did it fail? It fails. Right. It fails here. And so, you know, choice 1, get it in cubic form, use your calculator. Choice 2, try the simplifying assumption. Unfortunately, it fails. Choice 3, successive approximations. So how many guesses did it take you, the ones who figured it out? How many guesses did you get it in? Well, anyway, with successive approximations is it does take time. Usually what I do on tests, especially more so in Chem 1B than in Chem 1A, is I'll throw a bonus problem on there. You know, the people who are quick to throw a bonus problem, which is usually a more challenging problem. Like, for example, successive approximations or something like that. You know? But anyway, with successive approximations, we need a good first guess. So the first thing is we'll probably go 4x cubed on the top, and I'll leave it at 1.00 minus 2x quantity squared on the bottom. This is equal to 0.288. What's your first guess for x? What was your first guess? Who solved this? What was your first guess for x?
How do you determine what's a good starting point?
That's my question to you. I mentioned it last week. And so how many people remember what I said last week? Right, okay, at least three people got it. Use the simplifying assumption value x as your starting point, right? See, so the thing is, the test is tomorrow. This was last week's stuff. You should have already had it down, or at least seen it, at least once, or twice. But if you can't recall it, then you're sitting on the test with a blank page in front of you thinking, okay, where do I go from here? It's not like being a genius or anything. It's just putting in the time before, to make sure you're mentally prepared for this. It should be quick because, in time tests, your first x should be, well, we should do this. Do the quick calculation and do it.
4416.
What is it?
4416.
0.416. Yeah. So we do the simplifying assumption and we get some x value like this. Not that this x value is going to be particularly good, because the simplifying assumption probably was way off. Way off. But, just try it. And so we don't need 0.416. Let's just go with 0.4 because I know it's going to be way off anyway. And so might as well keep the numbers simple, right? And so if we plug in 0.4 cubed times 4 divided by parentheses 1 minus 0.4, which is going to be 0.6 squared. And so what does k come out to? Or what does this number come out to? What is it? 0.7. Wow, way off. Do you see that? 0.7? 1. All right, then we're way too big. Do you see that? And so let's try 0.3. You got it?
Yeah.
Also, if you're fast with the calculator, it helps too. I see some people when they enter scientific notation, I don't know how many keys they key in. They go, and they go like 1.00. Do you need the 0.00 for your calculator? No, so 1, and then they go times, and then 10, and then they raise that to this power. I'm thinking, wow, that's a lot of keystrokes just for. It should be quick, and so think about that for speed. .675, still way too big. Or
That one was for the
oh, 0.675 here.
0.4. We get. I got something.
0.711. All right. We're still way too big. So what do you want to guess for your next one? 0.2 or 0.1? Let's go with 0.1. What do you get for your k?
The first K,
The first K.
Point what?
0.64.
0.64.
6.4.
6.4.
Yeah.
What? Just like ignore it then, because we don't use it.
Hmm?
Just ignore it because we don't use it.
Yeah, we don't. No, we need to know the direction, but
But here we.
it's all right. Yeah, let's just keep going. Here, I'm gonna pull out my calculator. All right. So with 0.1, this is what I do. I just go 0.1 cubed. Does somebody have it already?
Yeah,
Okay, go ahead.
it's too small.
0.00625. Oh, we're way too small.
So two.
Okay, let's try 0.2. Point what? 0.088.
Yes.
Wow. Is 0.3 correct?
Yeah.
Okay, then let's go with between 0.2 and 0.3.
So 2.5.
2.5. All right. Let's go with 2.5. Oh, that's getting close. 0.25. Just a little bit more, huh? 0.26 you want to do? All right, let's try 0.26. Since this is homework, you know, on homework you have lots of things available. You know what I do on homework? If this is our homework, I put this into Excel and just have Excel do all my calculations. It's easy. What is it? 0.305. But you know, you should go through it manually, like on the test. So between 25 and 26, it looks like maybe 255. So do you get the point here? And so we don't necessarily, do we have to finish this or not? No. Okay. So just continue with this until you get it. Now once you get it, we aren't done with x. You know, once we have the x value, and when do we stop? We're going to stop when we get it at 288, right? When we get it to 288, we're going to stop, and then we'll plug it in here to get the equilibrium. But how much cadmium reacts? How much cadmium reacts? So we have lots here minus how much? Minus x, right? And so x is the moles per liter that cadmium reacts. So we got to figure out how many moles. In other words, all this x came from the solid cadmium. And so here's our moles, and then we just use a little bit of stoichiometry to figure out how many moles of cadmium and then how many grams of cadmium. Does that make sense? Yes, and then you can finish it.
When we find x, do we need to consider the significant number? Like, for example, if I have 0, 2, 5, 6, but it doesn't 2, 5, like.
No, here we want to keep going. This is, you know, even though we will eventually round it to 2 decimal places, we want to keep going because we're given this to 3 sig figs, so we want to get it up to 3 sig figs.
My question was that if my x, if I find 3 sig figs, but it's not close enough, so should I go 4 sig figs instead?
Yes.
Still cannot?
Yes, yeah, you go. You keep going. Okay. Even though you're beyond here. In fact, you got to keep going to 4 because, you know, this extra we always carry, so you want it to where it rounds. It has no impact. We're only at 2. For sure you'd be going on based on the decimal places.
Will we round our final answer or just keep
No, you plug it in here and then you round it properly. You know? But you carry the extra digits so you can see what the number is. You get it to 0.288 or to at least, you know, 2 more decimals. You want it out here, you know, so where it makes no impact on this number when you change it. So pretty soon you're at 0.00003 versus 0.00004. That makes no impact. Right?
Professor, what is said about cadmium.
Okay, there are two ways to figure out the cadmium. One is, you know, even though we do this, right, it's minus x. We're losing x because of the stoichiometry. It's a 1 to 2 to 1 to 2 ratio. Or all this cadmium in solution came from the cadmium solid. So there's two ways we can figure out. We could just figure out what minus x is. That's moles per liter that goes into solution. We need to know how many liters. Well, we do know how many liters it was given to us. And therefore, we can figure out how many moles of cadmium went into solution. You know, or we can use this to figure it out. And just a little bit of stoichiometry. So let's say x. X is, let's say it's 0.255. So if x is 0.255, then the cadmium 2 plus is 0.255 molar. And then we have, how many liters was it? 0.350 liters of solution times 0.255 moles of cadmium 2 plus per liter. And then for every mole of cadmium 2 plus, 1 mole of cadmium solid must have been dissolved. It's a 1-to-1 mole ratio. All the cadmium came from cadmium solid, and then just times the molar mass of cadmium. You know, the molar mass of cadmium is 112.41 grams per mole. And that tells us how many grams of cadmium must have dissolved. Okay, so we need that amount minimum. Actually, we only need that amount. We don't have to have an excess as long as we can establish the equilibrium. Okay, other questions?
The two nitrogen monoxide reacting with the oxygen and produce the nitrogen dioxide, and the K equals 5.6 times channeling alkaline at 184 degree. Increase the total pressure by additional nitrogen gas. We'll figure the leak cycle.
Okay, it was what, 2 nitrogen monoxide
Monoxide, yeah. After the oxygen.
plus oxygen,
And the 2 nitrogen dioxide.
2 nitrogen dioxide.
And K equals 5.6 times 10, 5, oh, 5. Yeah, and at 184 degrees C. Yeah. And increasing the total pressure by adding the nitrogen gas will figure which cycle.
Okay.
What's the fraction?
So, what you have to ask yourself in a question like this is, we have NO. Right. NO is going to generate the pressure of NO here. And then we have O2. O2 generates the pressure of O2. And then we have NO2. And NO2 is going to exert its own pressure. And all these pressures are at equilibrium. And so now all of a sudden if we add some nitrogen gas, will the nitrogen gas increase or decrease the number of collisions for the blue particles against the wall? No.
But my question is, will the nitrogen gas react with oxygen? Like, because the temperature is 184 degrees. So
184 degrees, yes, that's elevated temperature. And you have to worry about that. You're saying a side reaction occurs.
Yeah.
So this is a trick question because the side reaction would be the reaction between nitrogen and oxygen. And so at the higher temperature, the nitrogen and oxygen will react to form 2 NOs. This is what you're worried about?
it might produce
Yeah.
nitrogen dioxide.
And so what happens is, if you have the nitrogen attacks the oxygen, thereby lowering the oxygen and shifting it to the left. That, that frequently happens. That frequently happens where something will attack something in the equilibrium and shift it. But you got to think, nitrogen and oxygen at 186 degrees C, 186 degrees C, is that all that? It's hot, but is that all that hot? And so, right, and so maybe I said this in the gases chapter a long time ago, but the only way you can get nitrogen and oxygen to react with each other, because nitrogen and oxygen and air form a very stable mixture. When we think about nitrogen and oxygen in air, nitrogen is like 80%, oxygen is like 20% in air. And do we worry about that mixture reacting? The only time we worry about that reaction mixture reacting is at extreme pressures and extreme temperatures. The extreme pressures and extreme temperatures are like in automobile engines. There's something called a piston, which compresses the gases, and the spark, which ignites the gases. And the gases would be, gasoline, vapor, and oxygen, right? And there you form a tiny bit of NOx, oxides of nitrogen, from that. And so one of the automobile emissions tests, they look for NOx. From nitrogen and oxygen in air reacting in your engine. But other than that, you don't really have to worry. Even at 184 degrees C, 184 degrees C is not that extreme of a temperature. At 184 degrees C, I would not worry about nitrogen reacting with oxygen. All right, but this is very sharp of you to worry about that, because there is a potential reaction, but that potential reaction doesn't occur until you get to very high temperatures and very high pressures. So it would have no impact on this. Nitrogen, remember nitrogen, does anybody remember the bond energy for nitrogen? It was the strongest bond on that chart in Chem 1A. What was it? For covalent bonds. I think it was the strongest bond, wasn't it? You guys usually look at the extremes, right? The weakest bond was about 67 on the chart. It was II, the iodine bond, and the strongest bond was nitrogen-nitrogen triple bond, and that was about 1,000 kilojoules per mole. It was 980 something kilojoules, which is 1,000. It's hard to break that bond. This is why I called nitrogen a pseudo. What did I call? Pseudo noble gas. When nitrogen's cheap, so I used to use lots of different gases to prevent reactions. One thing I couldn't use is air. If I had my reaction in air, air was too reactive because it has oxygen and it has water, and so most of the stuff I was working with was highly reactive. And so I had to do it in an air-free environment. Well, in an air-free environment, we had choices. We could do it. Helium was a popular choice. I didn't like helium because helium was. My preference was argon. I really liked argon because argon would form a blanket, and argon is more dense than air. So even if some air leaked in, it would be at the top rather than at the bottom. Helium, though, helium's so. Its density is so low, it always rises to the top. So anyway, that's for the expensive stuff, because argon is not cheap, helium is not cheap, and so the expensive stuff is that. But for the cheap stuff, I always use nitrogen. Although you have to worry because nitrogen is a little bit more reactive than, well, actually a heck of a lot more reactive than argon and helium. Helium is the least reactive. Ionization energy on helium is huge, right? What has the highest ionization energy on the periodic table? The highest ionization energy on the periodic table? Or helium, yeah. Remember, the ionization energy increases this way. So helium's at the top. So helium's the least reactive. Argon's quite a bit more reactive because argon's a lot bigger, its ionization energy is lower. In fact, xenon has an accessible ionization energy, so xenon is quite reactive to strong oxidizers like fluorine. So a lot of xenon compounds are known. There are some argon compounds that are known, but no helium compounds have been synthesized. You know, helium just doesn't give up that electron. Well, nitrogen has a fairly high ionization energy as well. It's a pseudo-noble gas. It does react with certain metals like lithium. You've got to be careful with. But other than that, it's a good alternative. And so nitrogen, you know, you got to think of, it's not reactive at all. Legumes, you know, people have been trying to fix nitrogen for a long time. That is, you know, make compounds of it. But it turns out, you know, biological systems are quite good at that with their enzymes.
So if we treat the nitrogen as a pseudo-local gas, so it should have no impact.
No impact, right.
But the answer, you want to give two choices.
What?
The right side or left side? No.
It won't increase the overall fragility.
Write it in. That was my mistake. It should have been no shift, and I forgot to correct that. Shoot. I was having trouble. With the because I lost all the original files, so I only had the PDF. So I was thinking, I was gonna buy the version that allows me to upgrade, make changes to the PDF, and that turned out to be $100. So then I thought, I'm not gonna buy it. And so then I used a drawing program. I put it in the drawing program. That was one of the things I was going to fix, but I forgot to fix it, so sorry. That one, yeah. And that goes. That holds for anything. If you're confident in your answer and you don't see your answer there, then write it in. Could have been my mistake. In this case, it was my mistake. Okay.
So if you take out nitrogen dioxide, it shifts. It doesn't change. It doesn't shift to the right.
If you take out nitrogen dioxide, it shifts to the right.
Yeah.
Right. Okay. So now I see the question. Yeah, we treat nitrogen as pseudo-noble gas.
But how do you know that nitrogen is triple bonded?
How do I know nitrogen is triple bonded?
All the time.
It's triple bonded all the time because nitrogen, both BB and MO give the same thing. If you do the MO diagram for nitrogen, you know, which MO do we, let's see how your memory is, you guys. Which MO do I do? 2S? Which one what comes next after sigma star 2S? The pies or the sigmas come next? The pies? The sigma? Sigma? Not that you have to have this memorized, but you got to think. You know, there's two ways you could do it, right? One way is you just memorize it. It's so easy to forget if you never use it, right? The other way is if you have a little bit of conceptual understanding. And so what was the reason why the sigma jumped above the pies again? See, if you have this little story in your mind, then it's a lot easier to remember. If you don't have any story, then it's gone. You know, I don't know. It's a coin toss, right? But you should have a little story about why there's the two different orders. What was the little story? It was the repulsions. Good, Adrian. And so what minimizes the repulsions? Having a higher Z or lower Z? This was the thing that was weird. Because you would think the higher Z you'd get greater repulsions because the higher Z pulls the orbitals in closer, makes the orbitals smaller, right? And so normally we expect with high Z tiny orbitals, you know, and so what?
The higher Z causes
Greater repulsions or the higher Z causes lower repulsions? This was the tricky thing about that story. Lower repulsions. The higher Z caused lower repulsions because okay. Explain it in terms of penetration. We use, remember we use penetration to explain this.
Oh, S orbitals are more penetrating, so the lower Z will have more S orbitals.
The s orbitals are more penetrating, right? And so what that means for the sigma versus, remember the competition is between what two orbitals? It's between the sigma 2s and the sigma 2p, right? Was that it? Yes? Yes, that was it. Remember the sigma 2s and the sigma 2p kind of occupied the same space. And so having the higher z pulled in the sigma 2s tight, whereas it didn't pull in the pi 2p's because they're less penetrating. And so they have more separate room, right? They have their own space. Versus at the lower Z, you know, both aren't that I mean, with the lower Z, this penetration and shielding, whatever. You go back and you can remember. The thing is, the reason I'm doing this is, it depends on your goal, you know. If your goal, and I know there are like, I told you about my pre-med friend that came to me because I'm a chem major, so he wanted me to help him review chem. Did I tell you about that? Yeah. You know, I realized, wow, this guy hasn't looked at anything in chemistry. He's forgotten everything, you know. And so how do you keep things fresh in your mind? I told you to start reviewing the stuff from the beginning of this class. But if your goal is like pre-med and take the MCAT, and MCAT's like 75% general chem, I heard, and like 25% organic. If your goal is to take the MCAT, you not only have to review this class, you also have to flip back to your Chem 1A notes and start reviewing those at a regular interval so this stuff stays fresh and you don't forget it, right? Otherwise it's easy to forget. And so this is another illustration because I couldn't help this guy. You know, he had to take a year off to actually, did he take a year? Maybe he took more than a year off to review everything. It's like relearning everything. And so to prevent you from getting in that same situation, you know, just flip back and how long does it take to reread your Chem 1A notes? It didn't take me very long. I kept all my notes, you know, in binder. So just flip through it, you know. He didn't have any notes. He threw away all his notes. I couldn't believe it. He was starting just from the book. This is just impossible. 1,000-page book. How are you going to review that? You know? And so just an illustration. This was a story that you can, you know, you can avoid for yourself. You don't want to be in that same boat. Well, fortunately, he had no problem, you know, taking a year off. But not everybody has that luxury. Well, anyway, which one do we use for N2? What comes next? The sigma? Yes, the sigma. Next. Sigma 2p, and then the pi 2p's, and then the pi star 2p's, and the sigma star 2p. So just filling it, and N2 is 10 electrons, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. What's the bond order here? 3. So yes, it does have a triple bond. Both valence bond and MO tell you the same thing. And which one would you rely more heavily on? Which one's more accurate? MO. So MO is triple bond. Yes, it has a triple bond and it stays there. You know, there's only thing that would break it is violent collision or something like that. You know, or something attacking it. But otherwise, it's not going to. You know, when you look at the electron cloud. Okay, other questions? Your test will be similar, you know, to the last test that was posted. Format-wise, questions will be different. You know. not that different because it's chapter 15. So we need to finish up chapter 16 and then we get started on 17. So it turns out there are different techniques that we use to solve for multiple equilibria. Before I finish that last problem we were looking at. The technique that we've been using so far is just, stepwise. Step 1, step 2, step 3. We install these in a stepwise fashion. Sometimes stepwise won't work, and we have to use something called simultaneous method. Simultaneous stepwise. Another technique is something called the combined method, but the combined method doesn't work for everything. And so what we have is, these are like the, what should I say? Like the 3 definitions for acids and bases. What are the 3 definitions for acids and bases? There's Arrhenius, Bronsted, and Lewis. Really, we only need one, right? The Lewis, because the Lewis is the most general and it encompasses all. Well, really, we only need one technique for solving several equilibria, multiple equilibria. This is it, the simultaneous. This is the general method, the most general method you could have. But just like Lewis, is Lewis easy to approach everything? No. And so we have some simplifications to this, The stepwise and the combined are simplifications of the simultaneous that we can do. We can use the stepwise technique when the K's, get successively smaller. Like, for example, things like this happen. This works well when, K1 for step, etc. There's a significant, like a 10 to the 3rd difference, here. The K's, then it kind of works. The combined works for very specific scenarios, like, this will be discussed in chapter 18, I think. But it only works under very limited applications. But when it does work, it's pretty much the only way you can solve the problem. Otherwise, it's too difficult. So what happens when the stepwise fails? When stepwise fails, then usually you try combine, but we haven't talked about combine. We aren't going to talk about it because that's much more advanced until we get to chapter 18. And so if stepwise fails, you have to go to simultaneous. When does stepwise fail? Well, we saw a stepwise failure in the last example we did, which was, what was the last example we did? Ammonium water, when the concentration was 1.0 times 10 to the minus 6 molar ammonia. And what was the problem there? Did you see how it failed? Typically what fails, how something fails is like this. If a step perturbs a previous step, perturbs, like in Le Chatelet's perturbation. So let's say step 2 screws up the equilibrium in step 1. Therefore, we got to go back and fix the equilibrium in step 1, but if you go back and fix the equilibrium in step 1, it's going to screw up the equilibrium in step 2, and we're in an endless loop. You know, we cannot come to a answer. This results in this endless loop. Well, why didn't we have an endless loop before? Because if I look at this with HCl, for example, we did 1.0 times 10 to the minus 8 molar HCl, right? And if I look at step 1 was, let's say, HCl hydrolyzed with water to form hydronium and chloride. And so here in step 1, we start off with 1.0 times 10 to the minus 8 molar. Did we do this one? Right? And this was 0, this was 0, so at equilibrium we had 0 molar and 1.0 times 10 to the minus 8 molar and 1.0 times 10 to the minus 8 molar. And then in step 2, how much more hydronium did we add to this? We added a huge amount, you know, 75%, or what was it, more than 90% of the total was added in step 2. And so what we ended up doing was we added 9.51 in step 2, etc. We added 9.51 plus 9.51 times 10 to the minus 8 molar. And so the total came out to 10.51 times 10 to the minus 8 molar at equilibrium for the hydronium. You recall this? And so here, we added a huge amount of hydronium in step 2. Is this going to screw up the equilibrium in step 1? Why not? Right, because nothing can perturb it. K is very large. If K is very large, it's always just a one-way reaction. In fact, we don't think of it as an equilibrium. We just think of it as proceeding one way forward. And so even if we do add a whole bunch of additional hydronium here, it's not going to shift it back. Okay, because K is very large, because K is very large, the addition of hydronium in step 2 does not perturb step 1. The addition of hydronium in step 2 does not perturb step 1. Now, this is different than the ammonia problem we did. 1.0 times 10 to the minus 6 molar, was it? Ammonia. The addition of hydroxide in step 2 perturbs step 1, because step 1, remember, was at equilibrium. We double checked the K. But now the double check fails. And so this is different. The addition of hydroxide, because this is a base rather than an acid, so we're dealing with hydroxide instead. The addition of hydroxide in step 2 means that the equilibrium in step 1 is no longer valid. Do you see that? I mean, if I made this, let's say I made this 10 to the minus 8 molar ammonia, then we have a huge addition of hydroxide in step 2. That huge addition of hydroxide is going to screw up step 1. So if that you try to recalculate K, it's going to be way off with the new hydroxide concentration. Does that make sense? And so how do we solve this kind of problem? no longer valid. How do we solve? We use the simultaneous method. All right, so let's set up the simultaneous method here. Just to show. We got ammonia and water. This is going to produce ammonium and hydroxide. This equilibrium is governed by Kb. B stands for base hydrolysis. And Kb was 1.8 times 10 to the minus 5. Okay. Now, we know certain things, like for example, we know how much ammonia we have to start with, 1.0 times 10 to the minus 8 molar here. But we also have this water equilibrium, H2O liquid plus H2O liquid here. This is going to produce hydronium and hydroxide. Now, how do we solve both of these simultaneously? The way we're going to solve both of these simultaneously is this. We need to come up with the same amount of hydroxide. You see, what ties these two equilibria together is the hydroxide concentration. And so at equilibrium, this hydroxide concentration at equilibrium must equal this hydroxide concentration at equilibrium. If the two hydroxide concentrations are different, then we can't have both at equilibrium. And so both of these have to share the exact same hydroxide concentration. Right? And so how do we get the same hydroxide? Well, both of these contribute hydroxide. So the ammonia is going to contribute hydroxide, and the water will contribute hydroxide. And so the way we're going to do this is we're going to say let Y equal the amount of hydroxide that we're going to get from the water. And so this is going to be 0. So there's going to be some hydroxide present. Okay, these have to be the same. Otherwise, what we need to do is when we double check the Ks, these equilibrium concentrations here have to check out to Kw. These equilibrium concentrations here have to check out to Kb. Now, if one of these has this hydroxide, and this one has a different hydroxide, then it's impossible because both are in the same solution. There's only one hydroxide concentration in this solution, and that is called the total hydroxide concentration. And so this is the total hydroxide here. This is the total hydroxide here. Now the total hydroxide, let's do the calculation and then you'll see. Okay. And so we're going to say Y is the hydroxide contribution from this step, and then plus X here. This is going to be plus X molar. This is going to be minus X molar here. So at equilibrium, I'm going to get 1.0 times 10 to the minus 8 minus X molar, X molar here, and then this. This hydroxide concentration is going to be Y plus X. And so when I find out what my X value is and my Y value is, I plug those in here and double check it. When I plug in these equilibrium concentrations, it should equal 1.8 times 10 to the minus 5. And if it does, good, then it's checked. This is at equilibrium. Step 1 is at equilibrium. But the problem is, if step 1 is at equilibrium, we've got to make sure that step 2 is under equilibrium too. Otherwise, there's going to be some kind of change, right? And so in order to get step 2, well, here, we say initially there's no hydronium, and there's going to be some hydroxide here. The hydroxide initially is going to come from step 1. How much hydroxide comes from step 1? Well, it's going to be X. And now we're going to go plus Y molar here, plus Y molar here. And so at equilibrium, we'll have Y molar hydronium from water hydrolysis or water ionization, and then we're going to have X plus Y. You know, X comes from step 1, Y comes from step 2. Now, do you see the two hydroxide concentrations will be the same as they must be in order for this to be simultaneously under equilibrium? Does that make sense? And so this just turns out to be an algebra problem. All we have is just two unknowns. If we have two unknowns, we need two equations. And so can you come up with two equations and then just solve for both X and Y? Well, it's a little tricky, but try it. Right? Solve for X and Y. Try this.
The similarity of the ammonia 10 to the negative 6 or 10 to the negative 8?
Oops, 10 to the negative 6. 10 to the negative 6. You could try it, and then once you get X and Y, you plug them in here and then double check this K and double check this K and make sure both are simultaneously at equilibrium. Well, solving for X and Y is a bit more work, right? A lot more algebra involved, and so it takes a lot more time to solve this compared to our usual. You know, this is even more time consuming than successive approximations usually. Are we good with this? So hopefully, you know, hopefully the stepwise works, because the stepwise is a heck of a lot less work. Heck of a lot less work, because once you start plugging this in, you'll see, wow, this is harder than it looked. And it just seems like a simple multivariable thing, you know, X and Y, but it's harder than it looks.
What is KW?
KW, you have to have memorized for the next, not tomorrow, but for the next test. Yeah, 1.0 times 10 to the negative 14. Does KW, what temperature is that? It's 25 degrees C. KW is going to change with temperature. Does KW get bigger at higher temperatures or smaller at higher temperatures? This should be automatic, because you should have seen this several times. Well, maybe not several. You're probably focusing on chapter 15. This should be automatic by the next test. You know, it should be automatic by the next test because you should have seen it several times. KW is going to get bigger or smaller at higher temperatures? Bigger. Of course, you'd have to explain why. So you want to think about it. And anyway, the explanation why is your little story for remembering it, right? How do you remember it? Well, the way I remember it is I know what's that curve called? The Maxwell-Boltzmann distribution, you know, or the thermal distribution curve, or the thermal energy curve, whatever you want to call it. It's my little way for remembering it. All right, let's look at polyprotic acids and bases. Oh, there's one other thing I needed to mention here, and that is, you know, we did ammonia already, right? Remember we did ammonia? We did the 0.100 molar ammonia. And in the 0.100 molar ammonia, what was the percent hydrolysis? One thing I forgot to mention for this. Do you recall the percent hydrolysis for 0.100 molar ammonia? You know, for 0.100 molar, you should be able to do the percent hydrolysis in your head. Because if we start off with 100 parts, how many parts did we lose? Also, you know, if I'm losing people, because I have a lot of former Chem 1A students here, but, you know, and I realize that my afternoon class is all new people, so if I'm losing you, let me know about certain things. I'll go back and talk about it.
You want the percent hydraulic?
Yeah.
The ammonia, the 0.1
Yes. What was it?
That's 1.33%.
1.33 or 1.34%, right? Now the question is isn't it the same here? If I got ammonia as 1.33% hydrolysis, shouldn't it, if it's ammonia, shouldn't it be 1.33 or 1.34%? We'll just call it 1.3% hydrolysis here. This is the hydrolysis of ammonia. So we calculated before, it came out 1.3%. Shouldn't it be 1.3% here? No. If you look at the percent hydrolysis here, it turns out to be way bigger. Way bigger. It came out more like 90% hydrolysis, if you notice it. It comes out like 90, wait a minute, it's a weak base. How could it be 90% hydrolyzed? You know, wouldn't that be strong? Well, it turns out is, let me do this. It turns out the percent hydrolysis for weak acids and weak bases depends on the concentration. It's not a fixed number. And the way I remember this is this graph here. This graph shows concentration versus percent hydrolysis or ionization. Yeah, it's asymptotic like this. Well, not totally asymptotic because it'll stop at 100%. And so as the weak base becomes less and less concentrated, or the weak acid becomes less and less concentrated, its percent hydrolysis goes way up. And so this is for weak. And so we can't use that number. Even though it was 1.3% for 0.100, it's going to be a different percent hydrolysis for a different initial concentration. Whereas for strong, it doesn't matter what the concentration is. For strong, it's always 100%. You know, K is very large, right? K, very large. When K is very large, then, you know, we think of the reaction as being one way. Like we said earlier, you know, it's not, nothing's going to perturb this. It's always going to be 100% ionized. All right, so strong behaves differently than weak here. And we saw it in this example where, you know, we add a significant amount of hydroxide or significant amount of hydronium, but it's not going to perturb it if the previous step was a strong. But if the previous step is weak, then it'll perturb it, meaning we'd have to go simultaneous. And so this is the percent hydrolysis curve. So yeah, this is hugely hydrolyzed. You'll see in your calculation, or you look back to the previous one. Even though the previous one is wrong, it's not terribly wrong. This is going to be much more accurate. You'll see it's quite hydrolyzed. So you have two simultaneous problems in your homework, you know, and you can pretty much tell what they're going to be. One of them is hydrogen cyanide, hydrocyanic acid. You know, it's like 1 × 10⁻⁹ molar weak acid. And the other is ammonia, just like what we just did. Very low concentration of ammonia. Now, let's come to polyprotic. We're talking. Polyprotic means, you know, it has more than one acidic hydrogen. Polybasic, what does that mean? Polybasic, we usually think of as being able to accept more than one proton. Polybasic doesn't necessarily mean it has more than one hydroxide. You know, because there are lots of other bases that contain no hydroxide. Look at the base chart there. And so, for example, phosphate, what would phosphate be? PO4 3 minus. Would that be a monobasic base, a dibasic base, or a tribasic base? This would be a tribasic base because it's capable of accepting 3 protons, 3 hydrogens to make H3PO4. And so this is a tribasic base.
So you said polybasic was being able to accept more than one
Proton.
Okay.
This is a tribasic base. So, you know, let's take a look at this tribasic base and see. So if we have this tribasic base in water, then the only place it's going to get protons is from water. And so what we have here is, do you think it attacks 3 waters simultaneously? 3 different waters at the same time and plucks 3 protons right off simultaneously? No. It's going to happen in steps. So stepwise makes sense because it'll collide with one water, and if the conditions are right, it'll break 1 proton off, right? And form what? Hydroxide. What is this? Is this a K? This is a KB because this is base hydrolysis, right? Base plus water. Now KB, what is KB for phosphate? Well, I need to look that up, but when I look at my chart here, do you see any KB values? No, all I see are Ka values. Well, there's a reason for that. The reason is we don't need a KB chart because of the conjugate relationship. Because of the conjugate relationship, it turns out that this, let me just write the conjugate relationship over here, that the Ka times Kb is equal to Kw if the acid and base are conjugate pairs. And so the Kb will equal the Kw divided by the Ka. Now we've got to figure out what is the conjugate acid of this base. Yes, right. Here's the base, here's its conjugate acid, HPO4 2 minus. Do we have the Ka for HPO4 2 minus? Yes, it's on the chart. Do we know what Kw is? Yes, we've memorized it. And so we don't need a Kb chart. We could figure out the Kb for everything based on a Ka chart. And so we call this one Kb1 for phosphate, which is equal to Kb for phosphate. Let's try some more. And so this we typically call step 1. Actually, maybe we should do this. Should we do this? And do this for phosphate? All right, let's try it for phosphate. So this would be an example of or should we do an acid? Oh, maybe we'll do both. Okay. All right, let's say I had a 0.100 molar sodium phosphate solution. Is sodium phosphate the base? Normally when I think about sodium phosphate, I think salt, a sodium salt. What do you know about sodium salts? They dissolve, and are they strong electrolytes, weak electrolytes, or non-electrolytes? Strong electrolytes. So normally when I think about sodium phosphate, I have a step before this. I'll call it step I. That is, sodium phosphate is a soluble, strong electrolyte, which means it's going to go to 3 sodiums and a phosphate. This is an ideal solution, of course. We know in non-ideal solutions what would happen. Interionic attractions. Now, would sodium phosphate be a good candidate for deviation from non-ideal behavior? No. Why? No, because sodium ions, sodium ions are not that high of charge density, right? They aren't that strong of an interaction. Or, yes, because phosphate's highly charged. And so, I would say yes, because phosphate is a 3-. Are we going to worry about interionic attractions? Are we going to calculate activities? No. And so we're just going to assume perfect ideal behavior. With perfect ideal behavior, we start off with 0.100 molar here. And now, this. K is very large for strong. K is very large for strong. Strong electrolytes, i.e. strong acids, strong bases, and soluble salts. Right? And so I treat this as not a base, I treat this as a strong electrolyte. What's going to happen? Well, a strong electrolyte is going to ionize 100% to 0 molar molecules, 0.300 molar sodium, and 0.100 molar phosphate. So the same thing I do for something like sodium hydroxide. I don't really think of sodium, initially when I think of sodium hydroxide, yes it is a strong base, but initially when I think of sodium hydroxide I think soluble salt. The sodium ions and the hydroxide separate. And then I think hydroxide, strong base. Strong bases do what? Hydrolyze. Did this hydrolyze? This is a base. Did it hydrolyze? No, because it's a soluble salt. Now I have base. What is my base? My base is phosphate. Now I look at step 1. Step 1 is base hydrolysis, right? Base hydrolysis. So I do the exact same thing for sodium hydroxide. I would just step I, and then now we got our step 1 here. Our step 1, this is the end of line for sodium. So I know the sodium concentration in here. I should have 0.300 molar sodium ions. That's not going to change here, but what's going to change is my phosphate. Am I going to have 0.100? No, because base hydrolysis. I'm going to lose some phosphate to hydrolysis to make some other stuff. And so here, initial, I have 0.100 molar. 0 molar, 0 molar. Water, what should I put for the molarity of water?
0.
Nothing. Do you know what the molarity of pure water is? A liter of water weighs 1,000 grams. 1,000 grams is 55.5 moles of water. And so pure water is 55.5 molar. It's not 1 molar. 1 mole of water only weighs 18 grams. If you have a liter, it's 1,000 grams. So it's 55.5 molar. But its activity is 1. Okay, so here the change is minus x, plus x, plus x. And so at equilibrium we got 0.100 minus x molar, x molar, and x molar. Now let's calculate our Kb value. We need our Kb value for this. And so let's plug in some numbers here. This. 1.0 times 10 to the minus 14 divided by Ka. Actually, you know what? 2.2 times 10 to the minus. Does somebody have their book? Let's use the Ka values in our book because these Ka values are a little older since they haven't updated them. So let's take a look at the Ka for HPO4 2 minus. It'd be in chapter 16. In the middle part where they talk about polyprotic acids. How late do we go till today?
55.
55. Where did the time go? Wasted. I'm behind schedule.
You said
Hmm? Ka for HPO4 2 minus. It says, look it up here. It says 2.2 times 10 to the minus 13. I just want to see what it says in our book. 3, 4.2 times 10 to the negative 13. Yeah, let's use ours. 4.2 times 10 to the negative 13, which gives me a KB of 0.0238. Thanks. All right, so we'll plug this in here. This is going to be the monohydrogen phosphate times the hydroxide divided by the phosphate ion concentration here. And that is going to be X times X divided by 0.100 minus X. What do you think? Should we try the simplifying assumption? Yeah, it wouldn't hurt to try it because it's so quick. If we lose the X here, then it's just 0.0238 times 0.1 square root. So what does X come out to? .154. 0.154 is
No.
No.
It's
It's 0.04.
0.04.
No.
.0487. That's like a 48% change. It doesn't work. Doesn't work, which means we need to do the quadratic. But hopefully you have the quadratic solver on your calculator. Do you have that? If you don't have that, then on the test you got to add a little bit extra time so you could do the quadratic equation. Normally I do, you know, like I said, I'm not a strictly time one to keep track, you know, pencils down, pencils up type, you know. But you got to prepare though for that sometime. So anyway, getting this into quadratic form, we're going to have x squared minus, so we'll go plus 0.0238x, and then 0.1 would be 0.00238, minus 0.00238, which is equal to 0. And so plug in A, which is 1, B, which is 0.0238, and C, which is negative 0.00238, and we get our x value of 0.0383. Okay. So it wasn't 48%. It was only 38%, which is a huge difference, right? And so at equilibrium, I'm going to get 0.0383. Oops.
0.1
Yeah, 0.100. Equals 0.100 minus 0.0383, which is going to be 0.0617 molar. And then my HPO4 2 minus 0.0383 molar, and my hydroxide 0.0383 molar. Here. Right? Now we double check these to make sure. And so you do your double check. K is equal to 0.02377, which is good, right? That's good. That's good. So this looks good. Now we got to figure out what we're going to do in the next step, if anything. And so in the next step, what should we do? Oh, wait a minute. We just looked at this. This is a, what is that? That's an acid, right? This is an acid. So maybe we should do a Ka. Since we're generating this acid, we got to figure out how much hydronium is generated from this acid. Now hydronium is going to cancel out some of that hydroxide, isn't it? So should we do this step 2? Step 2. Step 2, well, actually HPO4 2- isn't just an acid. HPO4 2- occurs on both sides of this chart. Do you see that? In fact, HPO4 2- we call amphoteric. And so HPO4 2- is amphoteric, which means if it's amphoteric, there's a Ka and a Kb. So what do we need to do? Do we do the Ka followed by the Kb? Or only the Ka or only the Kb? Or the Kb followed by the Ka?
Only whichever value gives more of a reactor.
We pick the biggest value? If Ka is bigger than Kb, we pick that? Well, we have the value. Do we have it? Let's see. If the Ka, we just looked up the Ka for this. It's 4.2 times 10 to the minus 13. What is the Kb for HPO4 2-?
2.2.
Is the Kb 0.0238? Because we have that relationship, Ka times Kb is equal to Kw. No. No, this is the wrong acid. This is for the, wrong, yeah. That's for phosphate. This is for HPO4 2-. And so the Kb for this is equal to the Kw divided by the Ka for, no, okay, if this is the base, what is its conjugate acid? H2PO4-, dihydrogen phosphate. Which means that this is going to be 1.0 times 10 to the minus 14 divided by, what is the Ka? We should get this from our book rather than the... Do you see why I'm doing this? Why I'm doing this is because there are a lot of mistakes people make. When I go through this, Oh, go ahead. Okay, let me continue with that thought. We're out of time. The reason I'm going through this is because normally I can solve this problem and avoid all these tangents, all these wrong paths, right? Because I've done it so many times. I know the path through the jungle. This is my jungle analogy. But a lot of students don't know the correct path through the jungle, and they end up going down all these tangents here, right? And going through dead ends and other things. You know, so I do this in class. Normally when I do this in class, I forget all those stuff. I don't want to go that way. I don't want to do this because I know it's wrong. But do you? The problem is you don't. A lot of people don't, and then on the test, then I see it. Oh, they went this path. Why did they go there? You know, why didn't they follow my path through the jungle? Well, it's probably because they don't know the path. And so this is why we want to see all the different variations, all the paths, and see why that's a dead end, why that's a dead end, right? Why this is wasting time. Because if you know the path, you know, then you can waste a lot of time avoiding all these dead end paths. Okay, we'll stop here.